So what occurs when we're looking at a reaction that's not under standard state conditions, like 1 molar or 1 atmosphere pressure? How are we going to calculate the delta G for that type of reaction? Well, if that's the case, and we have different concentrations or pressures, we need to use delta G for non-standard conditions. And notice that doesn't have the degree sign as a superscript. And that delta G is going to be given by delta G naught plus RT ln of Q. And we know Q is just that reaction quotient that we've talked about in the past. So if we're doing something like the Haber process, then it would be important that we go ahead and take into account the equilibrium or the reaction quotient that we could write for that particular reaction being the partial pressure of ammonia squared divided by the quantity of the partial pressure of nitrogen times the partial pressure of hydrogen cubed. And we would have to still have that delta G naught that we'd calculate from their standard states, but then we would have to put in the reaction quotient and multiply it by RT in order to figure out what the actual delta G is for that. So let's take a look at calculating the delta G for the formation of ethylene from carbon and hydrogen at 25 degrees Celsius, and their partial pressures are 100 atmospheres for hydrogen and 0.1 atmospheres for ethylene. This is not under standard state conditions, and so, since our pressures are different here, and so we need to calculate what delta G is for this reaction. So if we look at the reaction, it's 2 carbon that are solid reacting with 2 hydrogen to form C2H4. The delta G for this reaction is 68.1 kilojoules per mole. If we wish to calculate ln of Q, then we have to basically calculate Q, or the reaction quotient. And that's just going to be the partial pressure of ethylene divided by the square value of the partial pressure of hydrogen. And just notice that the carbon is left out of the denominator there simply because it's solid, so we leave it out of this. So we get 0.1 over 100 squared. That gives us 1 times 10 to the minus 5. And if we go ahead and look at what ln of Q is for that value, we get a negative 11.51. If we go ahead and then calculate delta G for this reaction, then delta G is going to be that delta G naught value of 68.1 kilojoules per mole plus the 8.3145 joules per mole Kelvin for R. Temperature is 298 Kelvin, and the ln of Q is a negative 11.51. I also incorporated a 1 kilojoule over 1,000 joules in there just because we have to make sure our units work out. And so we end up with 39.6 kilojoules per mole. This reaction is not spontaneous under the specified conditions that we have because delta G is positive. So if we look at a reaction and we have most of the reaction mixture as reactants, then what we expect is Q is going to be much, much less than 1. And that means RT ln of Q is also going to give us a value that's much, much less than 0. And delta G is likely to be less than 0 as a result of that, indicating that a reaction wants to go and proceed in the forward direction towards the product side. What happens when we're all looking at a reaction mixture that's mostly products? And I should mention the other thing is that we are minimizing our free energy here as that reaction proceeds. You're trying to just minimize that delta G value. And so if we look again at sort of this reaction that's mostly products, then Q is going to be much, much greater than 1. That means RT ln of Q is going to be a value that's much greater than 0. And that means that delta G is going to be greater than 0 when we're mostly products. And so if that's the case, the free energy is going to be minimized if we have the reaction proceed to the reactant side. And so here you can see free energy in this chemical equilibrium. One way that we can kind of think of delta G is, because if you look at it, we have the total free energy of reactants and products on the left-hand side. And the reaction is always trying to proceed to the equilibrium mixture where free energy of the reactants and products is minimized. So it's almost, you can see why well, I guess we haven't introduced it here, but sometimes this delta G in a per molar quantity is considered a chemical potential. And you can see it's sort of corollary or correlation between chemical potential, since it's always trying to minimize the sort of potential energy, just like a ball trying to roll down a hill and minimize its potential energy. Okay, so this clicker question is asking you which one of these reactions is going to give you, or these reaction mixtures is going to have the largest delta G of reaction. And it gives us this fancy word that this reaction is endergonic, meaning that delta G is just greater than 0. And so we're going to consider the A molecules to be represented as just, or the red atoms to be A, and the blue atoms to be B. And if we go ahead and enumerate all of these, we can figure out the first mixture has 3A2, 3B2s, and 3ABs. The second one has 5A2s, 3B2s, and 1AB. And the last one has 1A2, 2B2s, and 6AB. Well, so if delta G is what we're looking for, and we know delta G naught, that's a positive value already, and it's the same for all of these different mixtures. And then we have plus RT ln a Q. Now the RT is going to be the same for all of them. So the only thing that's factoring into what's going to be the largest is that ln a Q. If it has a large ln a Q, then it's going to give a large value for delta G. If it has a small one, it's going to be smaller. So we should probably go ahead and write down what is exactly Q. And for this reaction, we have Q equals just this AB concentration squared divided by the A concentration and that B2 concentration that we have there. And so if we go ahead and calculate our value for Q for each one of these, the Q we get for the top one there, or not the top one, but A, is just going to be 9, because we're doing AB squared, and then we have just the denominator, we have 9 because it's 3 times 3, so we just get 1 here. For the second one, we have 1AB, so that's just going to be 1, and it's just going to be 3 times 5, so that's just going to give us 1/15 for this one. And then our last one here, we have 6, we can square that, that's going to give us 36, and it's going to give us 1 times 2, which just is going to give us 18. But that means this is the value that we're looking for our largest value for delta G. So we've looked at the delta G equals delta G naught plus RT ln a Q. When we're looking at equilibrium, we're saying that delta G has to be 0. And we also know that Q equals K at equilibrium. And so if we go ahead and plug in that value of Q equals K, and then we say 0 equals delta G naught plus RT ln a Q, and then just rearrange this, we're going to end up with delta G naught equals minus RT ln a K is one way that we can express that delta G. And then just to sort of see how that relates to what we know when delta G naught is less than 0, as you see in the chart, K is much greater than 1, and our equilibrium mixture is going to favor the products. When delta G is much greater than 0, K is going to be less than 1, and the equilibrium mixture is going to be mostly reactants. And if we're at delta G naught equals 0, then we're just saying that K equals 1, and really we just have a fair mixture of both reactants and products present. Okay, so in this one it's asking us when delta G equals 0, what's true here? So one of those states that the equilibrium constant is 1. Well, remember, it's delta G equals delta G naught plus RT ln of Q. And so when the equilibrium constant is 1, what we can expect is that'll be minus RT ln of K, and K is 1. We're going to get 0 for that quantity. However, we still are left with RT ln of Q, so that doesn't ensure that delta G equals 0. So that's not true. B, the system is reached equilibrium. That actually seems pretty reasonable, because when we're at delta G equals 0, we're supposed to be at equilibrium. That is true. C, the reaction will be too slow to observe. that one, we shouldn't expect delta G to say anything about the rate of reaction. And so now we are left with D and E are not correct, so B is the one that we want to go with for this particular problem. So another clicker question, it gives you N2O4 at 298 Kelvin, and in this drawing we have 8 NO2s and we have 3 N2O4s, and it asks us which statement is correct. And so it says, is the reaction at equilibrium? The reaction must proceed to towards reactants to achieve equilibrium, or does it have to proceed to products to achieve equilibrium? So how do we figure this out? We know that the Gibbs free energy change is 5 kilojoules per mole. And so we can go ahead and calculate what this would have to be with our current values for Q that we could calculate here. So we know Q, if we have 8 NO2s and 3 N2O4s, and the reaction yields 2 NO2s, then it's going to be that 8 value squared divided by 3. So we get Q equals 21.33. So we go ahead and plug in what that delta G is. We know it's 5 kilojoules per mole. We know the temperature, and we also know our value for R. So we plugging that all in, we end up with delta G is 12.6 kilojoules per mole. So if it's greater than 0, then it's not spontaneous to go to the product side. It wants to go to the reactant side. So B should be our correct answer in this case. So in this particular reaction, we're looking at finding the value for K, or the equilibrium constant, at 25 degrees Celsius. And we're doing it for calcium carbonate decomposing into calcium oxide and CO2. That's a balanced reaction. If we go ahead and look at what our delta G's are for each of those values, say in a table, back of the book, somewhere, we end up with those 3 different values. So it's going to be products minus reactants as we've done before. And when we calculate the delta G for that, just remembering the 1 moles out in front, we end up with 131.4 kilojoules. And so if we now want to calculate what K is, we have to recall that relationship we had there, that delta G naught is equal to minus RT ln of K. And we have to just rearrange that in order to figure out what K is. So solving for that, we're going to end up with E to the minus delta G naught over RT. Notice I put the delta G term in terms of joules, just to make sure that the joules cancel with the joules and the R, or the gas constant. Alternatively, you could put the gas constant in kilojoules per mole Kelvin if you wanted. So anyhow, we end up with a minus 131,400 joules divided by the product to 8.3145 times 298, and then we get a value of 9.29 times 10 to the minus 24. So let's look at a problem where it's looking at the formation of some dipeptide. I'm not even going to try saying that because I am not a biochemist. And in any case, it gives us a delta G, a formation of 13 kilojoules per mole. It says, what's the equilibrium constant for this? And so, again, we're going to go K equals minus delta G over RT, and you're going to plug in your values there, that minus 13,000 divided by 8.3145 times 298, and we end up with 5.3 times 10 to the minus 3. Which is E in this particular problem. Another clicker question. This one is giving us ethylene with water to form ethanol. And so it gives us the different delta G's of formation of all the different ones respectively. And so then we have to basically just figure out what the delta G values are here. And so the delta G naughts, I just wrote above each molecule, so maybe it's a little bit more clear. Now we can go ahead and calculate the delta G naught of this particular reaction. And then we're doing the same thing we did before by calculating K and that's just going to be equal to e to the minus delta g naught over RT. Plugging in our values there, make sure we are conscious of the minus there. And so that quantity up top is going to be a positive value, and we end up with 10.4. And then so that would be D in this particular problem.